that's known has some sort of drawback, limitation, complexity that you have to deal with. You just have to deal with it one way or the other. These are very simple, and as you can see, these are literally just on components soldered to the ends of wires. There is an infrared LED, which just looks like an LED that's turned off, even when it's working. Inside the little heat shrink shroud is a smaller phototransistor, infrared phototransistor. When it detects, or when infrared light shines on it, it starts to conduct. The way it's used in this circuit, it actually pulls the voltage down. It's pulled up normally when there's no infrared, and the more infrared that shines onto it, the lower the voltage goes. We can measure that voltage and then know how much infrared is on there. The algorithm is actually fairly simple. You measure how much infrared is in the ambient environment, that is with the LED turned off. Then you turn on the LED and see how much difference there is. So that means, is there something here or is there not? If it's reflective to IR and it's close enough and all these other constraints. It's still a fairly simple circuit, fairly reliable circuit once you get it set up correctly. And most of you all have probably seen something very similar to this or worked with other types of things. You can actually get already molded together little pieces that have the infrared emitter and detector in a single unit. It's already lined up. Won't suffer from alignment problems like these might. You can also design your board so that the LEDs mount straight to the board and then turn upside down and face. But this model over here actually has that. It actually has two dedicated PC boards, to do that function and to keep it, rigid, not bouncing up and down. So, like I said, it's evolving. And like I said, now this is going to be an analog voltage that measures how much infrared is coming back. So we'll need to be able to measure analog voltages. Our outputs. Some of you may recognize this little robot, little prize-winning robot from
the outdoor contest.
Yes.
It competed.
Yes, it did. It did compete. Yes, it certainly did. Yes, and won a gold medal.
Yes, you did win a gold medal.
Yes, a gold medal with a ribbon. 2 motors with wheels on it, and then an unpowered caster. There's the unpowered caster. Here's the wheels. Now, very popular format for building a simple robot because it's stable even when it's powered off. Easy to build. I'm not saying go out and make your own wheels. That's tricky, okay? But it's, when I say build, it means you can get something. You can buy it, acquire it, repurpose it, use something else. There's lots of wheels around us in consumer products. It's tolerant of misalignment and mathematically elegant. You can get into a lot of the math about how to control these and to know where you are in almost any space. Like if you want to measure it in X and Y displacement in the Cartesian plane, very easy to do with a minimal amount of feedback. Also, as far as controlling the speed and direction of the motors, very simple to do mathematically. If it's mathematically elegant, that will make it algorithmically elegant. You won't have a bunch of weird code that does a bunch of exceptions and constants that just come out of nowhere. If your original design uses mathematically elegant components, your code will improve. It will benefit from that. So these are the outputs. We saw the inputs that we wanted to use. We saw the outputs. That will accomplish, it should be all we need to move around but not fall off the edge, because we can pick up a reflection here, but when it gets over here it doesn't pick up that reflection. You can detect the edge. Now what would be nice is if it also had a detector in the back, so when it's in a corner and he goes, oh, I'm in a corner, I need to back up, help, I'm falling. Okay, it was just a simulation. No robots were harmed. This, it would help if there was one more for when it was going backwards. When we'll get into, that's not, we couldn't do that with this generation of the thing, but it's certainly possible using the same components, just rearranged a little bit differently. Using the motors, who is not familiar with servos? Who is not familiar with continuous rotation servos? Okay, I don't have to cover all that. That's what we're using because, as Paul pointed out earlier, when you buy a servo, not only are you getting a gear motor, which is a nice thing to have by itself, you're also getting the H-bridge, which is a reversible control circuit, electronic circuit that can actually make go forward or backward. And you actually get a little control circuit on top of that that will let you send just a single pulse to it to tell it which way to go, how far to go, how fast to go, all encoded in a single pulse. That's a nice thing about these little microcontrollers that we use is they're very good at sending out little coded pulses to things with very little software. But we'll get to that. Okay, mobile power source. We saw that one little block on the bottom. We're going to use batteries. This one uses 4 AA's. Yes, please. That one uses 3 AA's. So anything between 3 volts and 6 volts is plenty to run servos, your controller, your sensors, and should go for hours and hours. Nice if you have a power switch. This one has one built into the board. Mine didn't, so I used a the actual battery box has a power switch on it, which is nice. And fuses. Need I say more? Anything bigger than this, and you would definitely want fuses. You can burn yourself on what's just the power that's stored in these. You short them directly across, you can cause some damage. They burn up, so you don't. Okay, and then the controller, it needs to have the following requirements. It doesn't have to be electronic, it doesn't have to be a computer, it could be anything. It does need to use very little power, though, because we're wanting this to be a little demo robot, and we don't want to constantly be recharging or constantly feeding batteries to it, or recharging the pressure accumulator or whatever it is, putting more coal in the fire. It needs to be low power, it needs to be low cost, so that we can get it to as many people as possible. Easy to program or configure, depending on how you're setting it up. Easy to learn how to program it, and to teach people that haven't ever programmed. It needs to be easy to reprogram it, not just one time. Because once upon a time we had parts you could program one time, then one time, and then you threw it away. It was wrong, and it needs to be reliable. Talk about some of the different things you can use. We're going to use. I use ATtiny13. It's actually the A revision. It's just a die shrink and less space, less power. This version, I believe, is using a Tiny85, which is in the same family, same form factor, same peripherals, more memory. It just has more memory, and it only costs 50 cents more.
Are exactly the same.
I'm sorry?
Containers are exactly the same price.
I wouldn't doubt it. The price differential is almost non-existent.
I think it was 30 cents when I was at Mauser last time.
Yeah, the chip I'm using is $1. These are around $1.25. Why you wouldn't use, the bigger part? I just happen to have lots and lots of these in stock.
You already picked the number for your book, so you have to use.
I'm not building 85 robots. Okay, all of them different, and not just variations on a theme.
That's why you picked the
13. Yes, tiny. There's 13 tiny robots, and they're all based on the Tiny13. And hopefully they won't cancel it like they did the Tiny 11, which was even more humble than this one. But they apparently weren't making enough money on it, so it's no longer in production. So now we have a little bit more refined block diagram of what our little robot could be. It's got the controller in the middle. It doesn't have to be in the middle. It's got some power. It's got some wheels, and left sensor and a right sensor. Hopefully I spelled everything right. I put the right stuff on the right side and left stuff on the left side. And so that actually covers that layout, and to a certain degree. What the other one?
We stole it.
Oh, okay. Fine, I can make another one. And so that's really all we need. Now, here's a schematic diagram of a controller board that works. It's actually this controller board and that controller board. They're identical. This is the board that was made or demonstrated last month on how to make printed circuit boards. And you can literally, this looks fairly complex. It looks like a lot of components, a lot of interconnects and things like that. But it boils down to a board, the size of a novelty postage stamp, special issue of some sort, a relatively small amount of real estate. This part here is the controller chip. It looks complicated because They put 6 pins on this side and 2 pins on that. It's really just an 8-pin dip. It's a very small chip, which you can see on the board. And the other components are just really brought out to headers, a lot of them for the LEDs, for the servo outputs. And like I said, the left servo is just a digital output that goes to the left servo and then the right servo, and then it gets power and ground through the connector. Very easy to interface. Now the question is, why was left servo connected to pin 5 and right servo connected to pin whatever? I can't read it. 6, sure. Let's call it 6. What goes into that? And I think that, I gotta get to those. There we go. It's gonna green dye, low resolution scum. Making connections. Now what we need, we know what we need. How do we know which pins do what? Because you read the data sheet. No way around it, guys. You're gonna have to break down, read the data sheet. Now, some of y'all have sworn that since you graduated, you were never gonna open another book. You have to. Some of you said, I'm never gonna eat another vegetable since I moved out of my mom's house, okay? And said, I'm never gonna read another book. Okay, to learn how to use this stuff, and squeeze out everything you need to be able to squeeze out of it, you need to read the data sheet, become familiar with what's in it. You can look at other people's code. You can look at other project documentation that's out there, because there's tons of, type in AVR robot or even just small robot,